Google's newest quantum result produced a signal that today's best classical methods may struggle to reproduce. More importantly, the experiment was designed so that researchers could test the signal instead of simply trusting a mountain of random-looking output. If the results survive scrutiny, Google may have crossed a more important line than raw speed. But one question decides whether this is a durable computational advantage or another benchmark that classical researchers eventually dismantle. Can the measured quantum behavior withstand every credible attempt to reproduce or explain it classically? For years, quantum computing has occupied a strange position. The hardware is real, and quantum processors can manipulate information in ways ordinary computers cannot directly imitate. Yet whenever a company announced a dramatic benchmark, classical researchers often returned with a better simulation, a smarter approximation, or a new way to frame the problem. That did not mean the quantum machines were fake. It meant the finish line moved whenever researchers discovered that the supposedly impossible classical task was merely extremely difficult. This history is why a runtime estimate alone is not enough. Saying that a quantum computer completed a task faster than the best-known classical method can be meaningful, but it does not prove that classical computers will never catch up. Algorithms improve. Hardware improves. Assumptions get challenged. Sometimes the benchmark itself turns out to favor the quantum machine in ways that limit what the comparison can tell us. Google's newer approach matters because it aims to remove one of the escape hatches that weakened earlier claims. Instead of producing an enormous output that is difficult to verify, the experiment leaves behind a narrower physical signal that researchers can measure, predict, and attack. Imagine a drop of dye spreading through water. The dye begins in a recognizable shape, then swirling motion stretches and mixes it until the original pattern appears lost. If you could reverse that motion with extraordinary precision, you might recover a trace of the starting pattern. The quantum version follows the same basic idea. Information begins in a known state. A complicated sequence of operations spreads that information across the processor. The experiment then attempts a controlled reversal with a carefully placed disturbance and measures how much of the original information returns. The entire claim rests on that final step, because this is where ordinary noise and genuine quantum scrambling should produce different behavior. The processor is not being rewarded for generating complexity or randomness. It is being tested for a specific pattern in how quantum information spreads, responds to a disturbance, and returns under reversal. That pattern is the evidence. This creates 3 moments of jeopardy. First, the processor must prepare the intended quantum state accurately enough to establish a reliable starting point. Second, it must scramble the information through a sufficiently complex sequence, preaching a regime that becomes difficult to track classically. Third, it must reverse the process precisely enough for the returning signal to survive. One of those stages can fail. Preparation errors can corrupt the starting state. Control errors can make the scrambling different from the intended calculation. Noise can erase the returning information. A simpler classical model might also imitate part of the signal, making the result look more quantum than it really is. That is why the decisive achievement is not merely creating a complicated state. It is recovering a structured and testable signal after the information has been scrambled. Earlier quantum benchmarks often produced outputs so large and intricate that verification became part of the problem. If a classical computer could not reproduce the output, researchers faced an uncomfortable question: how could anyone independently confirm that the quantum answer was correct? A measurable signal changes the argument. Independent researchers may not need to reproduce every detail of the quantum state. They can instead calculate predictions in accessible regimes, establish theoretical bounds, compare competing models, and test whether the signal changes as expected when the experiment is adjusted. This is the difficult middle that quantum benchmarking needs to reach. The task must be hard enough that classical reproduction becomes genuinely constrained, but structured enough that the quantum result remains testable. A task that is impossible to check proves very little. A task that is easy to check but easy to simulate proves very little. The value lies in combining classical difficulty with experimental accountability. Now we reach the claim behind the headline, and also the assumption most likely to bring it crashing down. A comparison with classical computing is always a comparison with the strongest methods currently known and tested. It is not a law declaring that no classical algorithm could ever succeed. Any estimate depends on choices about the simulation method, available hardware, acceptable approximation, required accuracy, and the particular feature of the quantum result being reproduced. The honest verdict is therefore narrower than saying, classical computers can never do this. The defensible claim is that the experiment appears to have entered a regime where reproducing the measured behavior with the strongest available classical methods becomes extraordinarily difficult. That wording sounds cautious, because it is. It also describes how scientific progress actually works. A durable quantum advantage should invite classical researchers to attack the comparison. If they find a shortcut, the field learns that the boundary lies farther away. If repeated attacks fail, confidence in the advantage grows. The hardware is central to that test. A quantum processor does not become useful simply by containing more qubits. The harder problem is preserving control as those qubits interact. Every operation can introduce an error. Every measurement can blur the result. As a calculation grows, small mistakes can accumulate until the quantum effect disappears beneath the noise. For this experiment to mean anything, the returning signal must remain larger and more structured than the errors trying to bury it. Researchers need to show that it persists across repeated trials, responds predictably when the setup changes, and cannot be explained adequately by a simple noise model. A single dramatic run would not establish that. A credible result must appear consistently enough to separate the intended effect from statistical luck, calibration drift measurement error, or a hidden shortcut in the analysis. This is where Google's claim either survives or dies. A huge estimate of classical difficulty means nothing if ordinary noise can fake the signal. The strongest alternative explanations need to be treated like competing cases. Perhaps imperfect control created a pattern that merely resembles the expected quantum behavior. Perhaps a simplified classical model captures the part of the output being measured. Perhaps the comparison assumes a level of accuracy that makes the classical task look harder than it needs to be. Perhaps the result depends on extrapolating beyond the regimes where direct comparison remains possible. A serious validation effort must vary the complexity of the experiment, examine how the signal changes, compare it with accessible classical calculations, model the effects of error, and disclose enough information for outside researchers to challenge the analysis. The evidence becomes stronger when one explanation predicts the pattern across multiple conditions while its rivals fail. It becomes stronger again when independent teams reproduce the measurement or reach the same conclusion using different methods. Without independent confirmation, the appropriate verdict remains provisional. Google may have demonstrated an important and testable quantum effect, but the broader claim of durable computational advantage stays open to challenge. That is not a dismissal of the work. It is the standard a claim this significant should face. So, has this result already produced a practical application? No, at least not on the evidence presented here. This is a scientific benchmark, not proof that quantum computers are ready to transform ordinary computing or solve commercial problems at scale. Classical computers will remain better for nearly everything people do each day. Any plausible quantum advantage is likely to begin in narrower domains, where quantum mechanics is part of the problem itself. The most direct bridge is using increasingly controllable quantum processors to study complex quantum systems that become prohibitively difficult to represent with conventional methods. That bridge still requires more than an impressive benchmark. A useful scientific experiment should first reproduce trusted results in a region where established measurements or calculations remain available. Researchers can then push the same method into a harder regime where conventional tools become too expensive, too approximate, or too slow. Agreement in the known region builds confidence. New information in the inaccessible region creates value. That is when a quantum processor stops being a machine that wins a race designed for itself and becomes an instrument for learning something that existing tools cannot reach. Google's result does not establish that full transition. What it may establish is a more credible route toward it. Prepare quantum information, drive it into a classically difficult regime, and recover a measurable signal that can still be tested against physics. The strongest skeptical objection remains the fairest one. Classical algorithms are still improving. History says that every bold quantum performance claim should trigger a search for better simulations, better approximations, and weaknesses in the comparison. That response is not an embarrassment for quantum computing. It is how the field discovers which claimed advantages are real and which depend on temporary limits in classical technique. The present verdict, therefore, has two parts. Google appears to have demonstrated a structured quantum experiment whose measured behavior may be extremely difficult for current classical methods to reproduce. It has not proved that classical computers can never match the result, that the finding has been independently settled, or that the experiment already delivers a practical application. That may sound less dramatic than declaring the quantum era complete, but it marks a meaningful change. The debate is moving away from whether a quantum processor can produce something unusual and toward whether the resulting physics survives increasingly hostile attempts to explain it away. If that standard is met, the important question will no longer be whether a quantum computer can win an artificial benchmark. It will be what researchers can learn once quantum hardware reaches places their classical tools cannot reliably follow. Like the video and subscribe for more clear explanations of emerging technology.